Okay, welcome back. So let's see where do we stop last time? So last time I had given this single example um, of this system, and I said that today that we would actually find a solution if solution exists, that we'll find it for this thing. So that's what I want to start doing first. Surprised no one recognized my, I guess that's what I get for being really old. Nobody liked my nice voodoo reference to video cards. Back in my day, they weren't called video cards. They were called 3D accelerators, and it was pretty rad to have one. So anyway, here's the system in question. If I look at the augmented matrix for that system, looks like this. I'm not going to draw in that line typically. This line is just drawn in, for your own comfort. So here's the augmented matrix that I've put here. I'm going to be constantly referring back to the system of equations that this augmented matrix corresponds to. Because as we work through these, it's good, at least when you're first starting to do this, to always think about what is being referred to here. So we have three elementary row operations we're allowed to do: replacement, interchange or swapping, and scaling. Okay, these are the three things I'm allowed to do. Now, why are these the three things and the only three things I'm allowed to do, and what is the purpose of any of this? So before I begin, maybe I should say on a different sheet before we start working here, is quick definition. If there exists a sequence of row operations taking an augmented matrix A to a matrix B. Okay. We say that A and B are row equivalent. Okay. So if you have two matrices and there exists a sequence, it doesn't matter how long it takes, there's some sequence that takes you from A to B, okay, by some number of row operations, okay, in whatever combination, then those matrices are said to be row equivalent. Okay. So, what is the nice thing about being row equivalent? There's a fact that is kind of the central fact in why we do all this stuff, so it's very important. That's why I put the stars there. So if the augmented matrices of two linear systems are row equivalent, then the two systems have the same solution set. So here is the central fact that is the reason why you would do row operations to begin with. The idea being that I can use a judicious choice of row operations here to take an augmented matrix and put it in a form that is nicer for whatever reason. And if I've used only row operations to do this, then the linear system corresponding to that augmented matrix in question has the same solutions as the one I started with. Okay, but for whatever reason, it is, simpler or easier to deal with. Okay, and so if I find solutions to this new transformed linear system, that's the same as finding solutions to the system I started with. So that answers whatever questions I had about that system. Okay. Okay. So going back, this is what we have. This corresponds to the system that I'll write out once more here at the top. So this corresponds to the system x sub 1 minus 2, x sub 2 plus x sub 3 is equal to 0. 2x sub 2 minus 8, x sub 3 is equal to 8. And 5x sub 1 minus 5x sub 3 is equal to 10. That is the system that this augmented matrix corresponds to. Now, I want to do row operations. In the context of trying to solve a problem like this, what are the row operations actually doing? As I said last time, the row operations, every single one of them, corresponds to something you're allowed to do to an equation or an equation in a system of equations. So what are those things? So replacement, as I said, is I can multiply one of these equations by whatever I want to, and then add it to any of the others to replace that equation that I'm adding it to. That's something I can do because these are all equations, right? There's all these equal signs here. That's something I can do. That might seem like the most complicated thing to do, but in a way, as we'll see later in the semester, it's actually the simplest of these. Interchange is I can swap the order of the equations. I can always do that, so that's easy to see. Scaling, I can take any of these equations and just multiply it by some non-zero constant. The reason it has to be non-zero is multiplying by 0 destroys all of the info in that equation. So if I took the third equation, multiplied both sides by 0, I get the equation 0 equals 0. That's always true, and I've basically taken my system of 3 equations and turned it into a system of 2 equations, and that's clearly not going to be good. That's getting rid of any info that third equation is telling me. Okay. All right. Yeah, so exactly. So what is the idea here? Okay, I'm going to use this notation's not used in the textbook, but I find it's a useful notation to keep track of everything that you've done so that, you know, if you're worried about getting this right when you're doing it, it's easy to check your work if you've done it this way. So what am I going to do? Looking at this, let's think, what would I do maybe to try to, what would I do to simplify this? Like, what was my brute force method for solving a linear system of equations? So you might remember Gaussian elimination. So the idea with Gaussian elimination was you used algebra to judiciously get rid of some of these variables one at a time until you took one of these equations to an equation involving only a single variable, which you could then solve because these are linear equations. So you could solve that single variable linear equation for one of the variables, and then you could back substitute into the other equations to be done, right? That was the ultimate goal. Okay, so what I'm going to do is use row operations to encode that in augmented matrices instead of doing the algebra, because doing the algebra would require me saying, well, let's see what it would require me to do. So what am I going to do here? And then we're going to talk about what my goal is and why I can say this. So first of all, what am I going to do? My first idea is I want to zero this out. Why? If you don't totally see the intuition for this, then you can wait until I explain reduced row echelon form here in a little bit. But the idea is that I start with x sub 1, and I want to get rid of the other copies of x sub 1 in these other equations. The idea being is eventually I want to isolate one of these equations to have only one variable. Say in the third equation, I only want x sub 3 to show up. Okay, I don't have to do it that way. I could have chosen that with any of these variables, but I'm going to do it this way just because of how they're numbered. Okay, so in order to do that, I want to use this x sub 1 to cancel out this 5x sub 1. So the row operations that I have at my disposal, I want to use replacement here. Okay, that's how I'm going to cancel these out. I am going to multiply the first equation by minus 5 and add it to the third equation here. Okay, so to keep track of that, I'm going to say that my first row operation is replacement. And replacement is going to be minus 5 times row 1 plus row 3. And in using this notation, the way that I interpret this is replacement, where I've multiplied minus 5 times row 1. I'm adding it to row 3, replacing row 3. So the thing that comes second in this replacement, or in this notation, is what gets replaced. So when I write this augmented matrix, the first two rows are unchanged. So this is 1, minus 2, 1, 0, 0, 2, minus 8, 8. Okay. So it's only the third row that's being changed here. So in order to see what the third row is, it's minus 5 times the first row plus the third row. So minus 5 times 1 plus 5 is 0. That's the entire purpose I chose minus 5 here. Minus 5 times minus 2 is 10 plus 0. That's 10. Oh no. Oh no, right? I took a 0, which is nice, and turned it into a 10 doing this. So I've actually went backwards in terms of complexity here. So we'll see that this is okay. This is fine. If you're not careful with this process, you will go in circles. If you don't have a nice plan, you will go in circles. But luckily, we have an algorithm you can follow that always works and will always make sure that you don't go in circles. Okay, minus 5 times 1 is minus 5, plus minus 5 is minus 10. Okay, that's nice. And then minus 5 times 0 is 0, plus 10 is 10. Okay. All right. So, what does this correspond to now? Well, it's the same equations as up here because these first two rows didn't change, but this bottom equation is the equation 10x sub 2 minus 10x sub 3 is equal to 10, right? So maybe I should write that here. So this corresponds to, this line corresponds to the equation 10x sub 2 minus 10x sub 3 is equal to 10. Okay. Now, what might I do here? Well, I can now make my life easier in the computation I need to do by scaling, right? I can scale the second and the third row to make these numbers nicer. And so when you get better at this, you'll be able to do these steps you'll be able to do multiple of these steps at once. So I'm going to scale row 2 and row 3 in the same step to save me time. So I'm going to multiply row 2 by 1/2, and I'm going to multiply row 3 by 1/10. All right, so I've done nothing to row 1, so row 1 is exactly the same, 1 minus 2, 1, 0. Row 2 becomes 0, 1, minus 4, 4. And row 3 becomes 0, 1, minus 1, 1. Okay, this just makes the arithmetic I have to do easier. Okay. Now, continuing on, what is my next step in the process? I'll explain this in a little bit. But my next step in the process is I said at the beginning, my goal was to turn this third equation into an equation that only involved x sub 3. So in order to do that, I have to turn this augmented matrix into a triangular matrix, meaning that I have a triangle of zeros in the bottom here, and hopefully a bunch of not so nasty numbers on this diagonal. Again, I'll talk about that a little bit later. So I continue on. I want to zero out the two entries above and below this one. Okay. Well, how do I do that? So my next step, I want to leave row 2 unchanged. So 0, 1, minus 4, 4, that's not going to change. The only thing that's going to change is rows 1 and rows 3. So I'm going to multiply. What would I need to multiply row 2 by in order to make row 1 nicer in this way? Well, I want to zero out this entry corresponding to the x sub 2 entry in here. Of course, I don't actually even have to do that. You know what? I'm not going to do that. I'm being too efficient. We'll save being that efficient till later. Okay, so I won't even mess with that. Okay, so no point doing that now. Although that will totally work perfectly fine. I mean, that is exactly how you would do it ideally, but we're not doing ideal right now. So let's just do the third row. Let's replace the third row. So let's zero this thing out. So in order to zero this entry out, what do? I would multiply row 2 by minus 1 and add it to row 3. So minus 1 times row 2 plus row 3, with the understanding that row 3 is the thing being replaced here. Okay. So minus 1 times row 2 is minus 1 times 0 is 0 plus 0 is 0. So that is unchanged. That's good. We'll see why that is always going to work out like this if you're careful, that the entries you care about aren't going to be disturbed by subsequent algebra that you do on them. So next, minus 1 times 1 is minus 1 plus 1 is 0. Good. That's exactly the purpose for choosing minus 1 here. Minus 1 times minus 4 is 4 plus 1, or plus minus 1 is 3. And minus 1 times 4 plus 1 is minus 3, I believe. Okay. And so I can make my life easier here by scaling this. I don't have to. In fact, let's not. Let's just check and see what's going on here. So let's rewrite the system. So the system I have is x sub 1 minus 2 x sub 2 plus x sub 3 is equal to 0. X sub 2 minus 4 x sub 3 is equal to 4. And the last one is 3x sub 3 is equal to minus 3. Okay. So here's my system. Now, according to this fact that I have written, where did I put that? Where did I have that written somewhere? Ah, here we go. According to this fact I wrote down earlier, right? If the augmented matrix of two linear systems are row equivalent, then the two systems have the same solution set. So this solution set that I started with that I wanted to solve has the same, this linear system that I wanted to solve, the solution set of this thing is the same as the solution set for this new system that I found. But this is easier because this last equation is really, really simple. So this last equation, 3x sub 3 is equal to minus 3, tells me what? So that tells me that x sub 3 is equal to minus 1. I get that immediately here. Then what? Then I can plug that in. This is the back substitution step in Gaussian elimination. Then I can plug this into the second equation, which only involves x sub 2 and x sub 3. So the second equation becomes x sub 2 minus 4 times minus 1 is equal to 4. So then x sub 2 plus 4 is equal to 4. So then x sub 2 has to be 0. Right? So x sub 3 has to be minus 1. Based on that, x sub 2 has to be 0. And then we can use the last, the first equation here to find x sub 1. So x sub 1 minus 2 times 0 plus minus 1 is equal to 0. But this means that x sub 1 is equal to 1. And so the system has solution that is, if I write it as a vector, which we'll talk about in a second, this is 1, 0, minus 1. Okay, or written as I've written here, x sub 1 is 1, x sub 2 is 0, x sub 3 is minus 1. Okay, so the point 1, 0, minus 3 is the solution, right, in R3. You want to think about it like that. Okay. Now, um, a couple of questions. So one, as someone noted, there's a lot of different ways that you could do any of this. So in fact, while I was doing it, I decided against doing some simplifications here, right? I was gonna originally zero out this thing and work from there, but I didn't do any of that. Even here, I didn't scale this last row, even though I could have, because it was easy enough to just look at this and solve this third equation. So there are a lot of ways that you can solve problems like this, okay? But in trying to categorize solutions and in trying to categorize what it is that's going on here, that might introduce some problems, right? If there's a ton of different ways, if there's a ton of different forms that this augmented matrix can take, then it can be difficult to talk about, say, things concerning behavior if there's just so many different forms an augmented matrix can take, right? So we started with an augmented matrix that only had these two zeros right here other than in this row. So in the coefficient matrix, there were these two zeros. But then we ended with a matrix that had more zeros. And with a bigger matrix, that would have been true as well. But then, so the question is trying to come up with describing the behavior of a system based on the matrices that show up. I need some way of being able to talk about a form a matrix has that allows me to make some statements, because if there's no nice unique form that I can talk about for these matrices, then I run into trouble since there's so many ways that these can be solved. So there needs to be, associated to any matrix like this, one nice unique form in some way that allows me to talk about whether or not, or allows me to talk about the behavior of a matrix. Okay, so to do that, I talk about row echelon form and reduce row echelon form. So before I do that, I'll ask questions about existence and uniqueness. So there's two fundamental questions that are asked about any linear system. So one, is the system consistent? Okay. So this is existence and uniqueness of solutions to linear systems. So is the system consistent? What does that mean? Remember what we said consistent means? That means at least one solution. So does it have at least one solution? Okay. All right. Sometimes the answer to that is no, right? So if the answer to that is no, well, then you stop there. But saying that it has at least one solution means, i.e., a solution exists. A solution exists is if it has at least one solution. But then natural question is, how many does it have, right? So is the solution unique? So the first question is a question of existence. Do solutions exist? The second is, do the solutions that exist from the first part, are they unique? Are they the only ones, right? Or are there more? Okay. Okay. So these are the fundamental questions for any linear system. We'll see that this is ultimately going to result in fact, let's just go ahead and do this before I talk about row echelon form. So let's do, so determine if the following system is consistent. Okay. right, so the system in question is x sub 2 minus 4, x sub 3 is equal to 8, and 2, x sub 1 minus 3, x sub 2 plus 2, x sub 3 is equal to 1, and 4, x sub 1 minus 8, x sub 2 plus 12, x sub 3 is equal to 1. Okay. Okay, so here's my system. The associated augmented matrix, I'm just going to copy down here. So this is 0, 1, minus 4, 8, 2, minus 3, 2, 1, and 4, minus 8, 12, 1. That's reading row-wise, not column-wise. Okay. Okay, now if I'm going to follow the same kind of process that I followed before, that is, ultimately I want to turn the third equation, or whatever equation ends up in this slot, is to only having the single variable x sub 3. So if I want to follow this procedure, then having a 0 here is not going to cut it. And so I want to swap those around. So I'm going to swap rows 1 and 2. So to swap rows 1 and 2, I'm going to just do this. So here's my symbol for swapping rows 1 and 2. So that is not going to change row 3 at all. Rows 1 and 2 get swapped. Okay, and now I'll proceed as before, right? So the idea is trying to zero out these things judiciously till I get a like triangle of zeros here, and then hopefully this last equation I get, you know, will have only a single variable, and then I'll solve that and back substitute like I did before, right? Okay, so what do I do next? I want to zero out this entry in the third row. So in order to do that, I would need to multiply row 1 by minus 2 and add it to row 3, replacing row 3. So minus 2 times row 1 plus row 3 is what I'm doing. Okay. So this is not going to change row 1 or row 2 at all, so I'm just going to go ahead and copy those. Okay, so then minus 2 times 2 is minus 4, plus 4 is 0. That, of course, is the entire reason I chose minus 2 to begin with, so that had better work out. Minus 2 times minus 3 is 6, plus minus 8 is minus 2. Minus 2 times 2 is minus 4, plus 12 is 8. And minus 2 times 1 is minus 2, plus 1 is minus 1. Okay. Okay. Yeah, so someone asked, why wouldn't you just swap row 3 instead of row 2? You can do that. You can do it that way. Yep. There's nothing stopping you from doing it that way. Okay. So ultimately, it's not going to matter how you do this, as long as you do it in a way that gets you to to termination, as long as it terminates. Now, I'm intentionally not doing this in the most efficient way here, because I'm about to introduce row echelon form, and that's gonna explain the process for doing it, and that's gonna give you like a concrete process to follow that's always going to terminate, and more or less is always going to be kind of the same process that you use. Okay. Okay. Can we do something like just taking a determinant? Oh, so that'll come later. There's a lot of reasons why taking a determinant is not always great, because for matrices that are bigger than 3 by 3, for instance, taking a determinant is kind of a nightmare if you're doing it by hand and not using some other method. So that's another thing. Also, taking the determinant alone would only tell you, whether or not it's consistent or inconsistent. It wouldn't actually find the solution for you. So that's another thing. Row echelon, yeah, that's it. That's how to spell it. That's how to say row echelon. I'm going to be writing that here in a little bit. Okay, so continuing on, what do I want to do here? So now that I'm here, I want to zero out this entry like I did before. I'm making that triangle of zeros just like I did in my last attempt here. So nothing's going to change in rows 1 or 2. I can go ahead and copy those. And then I'm going to do 2 times row 2 plus row 3. Okay, that's going to be what I'm doing to zero these out. So 2 times row 2, so 2 times 0 is 0, plus 0 is still 0. That's good. 2 times 1 is 2, plus minus 2 is 0. That's the entire purpose I chose 2. So that had better work out like that. 2 times minus 4 is minus 8. Plus 8 is 0. And 2 times 8 is 16. Plus minus 1 is 15. Okay, so I've definitely made that last row simpler. Okay. But it's good to, at this point, now that I've gotten to this triangle of zeros here, to translate this back into a system, right? So what system is this equivalent to? Every augmented matrix you see written down it corresponds to some system. So the system it corresponds to is 2x sub 1 minus 3x sub 2 plus 2x sub 3 is equal to 1. And 1x sub 2 minus 4x sub 3 is equal to 8. Why did I write 0 here? This is an 8. Okay, and lastly, 0 times x sub 1 plus 0 times x sub 2 plus 0 times x sub 3 is equal to 15. So this is the equation 0 is equal to 15. Right? But this is an issue, right? Because notice this doesn't depend on any of the x sub i's, right? This doesn't depend on x sub 1, x sub 2, or x sub 3. 0 is never equal to 15, right? But we followed the rules here, so we didn't make any arithmetic mistakes. So we followed the rules. We took a system that we wanted to determine whether or not it had a solution. We used row operations to translate it into a system that looks like this that has no solutions. So since these have to have the same solution set, that means that this has no solutions, right? So this is no good, and thus this has no solutions. i.e. is inconsistent. Okay. All right. Yeah, we'll get into how the determinant would tell you whether or not a matrix is consistent. And you wouldn't be taking a determinant of an augmented matrix anyway, because determinant only applies to a square matrix. You'd be taking a determinant of the coefficient matrix. But that's all chapter 3 stuff. We'll get into that stuff later. Okay. So this has no solutions. It's inconsistent. And the question is, when you are doing this process, if your system has no solutions, is this always something that comes up in the augmented matrix? Do you have a line like this? And the answer is yes. And so I just saw another question in the chat. Whenever you reduce a matrix to something that doesn't make sense in this way, yeah, assuming that you used row operations correctly, this is what you end up with. Okay, so this is what you end up with. Now, basically, this is, and I'm going to state this as an existence uniqueness theorem later, that you're always going to end up with a bad row like this if the system in question is inconsistent. Okay, so consistent means it has at least one solution. That's what consistent means. But a consistent equation sometimes doesn't have a unique solution, right? Because there's always three possibilities here. So three possibilities are it has infinitely many solutions, it has a single unique solution, or it has no solutions, right? Those are the possibilities. Okay. So the big thing is row echelon form. Okay. Okay. So here is the definition. So a rectangular matrix that is when we say rectangular, we mean m by n, not necessarily a square matrix. So a rectangular matrix is a matrix A that has m rows and n columns, right? That's what this means. Okay. So a rectangular matrix is in... The book calls this echelon form, but I'm going to call it row echelon form because of the command RREF. So this is in row echelon form. If it has the following three properties. Okay. So first property, all non-zero rows are above any rows of all zeros. A non-zero row is a row that has a single non-zero entry at least. Okay, so all non-zero rows are above any rows of all zeros. Of course, this is really easy to fix because if you are in a situation that violates this, you can just easily row swap your way out of that. Okay. So this one is kind of like the easiest to fix. So next thing is each leading entry of a row is in a column to the right of the leading entry. In the row above it, or of the row above it. Okay. All right. And yeah, for those asking, we'll see about mods for the stream. I toyed with the idea in some of my other large lectures of having some students having chat mod power. So yeah, we might do something like that. So what does this mean? This will make a little bit more sense after you see what's going on in an actual matrix. But I've used a word here that I didn't define yet, leading entry. What is leading entry? Leading entry is the leftmost non-zero entry in a row, right? So leading entry is the leftmost non-zero entry in a row. So anything that is a leading entry for some row is just the leftmost non-zero entry in a row. Okay. And the third thing that a matrix in row echelon form must satisfy is the following. So this is all entries in a column below a leading entry have to be 0. So all entries in a column below a leading entry are zeros. Okay. Next, so if a matrix is in row echelon form, so if it already satisfies these three properties. Oh, the question is, isn't it implied by the second rule? The answer is no. No, it's not. Okay. So I'll give examples of why this isn't. So the thing is, all three of these are needed. So if a matrix is in row echelon form, so if it satisfies these three, and additionally also satisfies the following two properties, it is said to be in reduced row echelon form. Okay. Also known as RREF. Okay. So I haven't said what those two properties are. So let's see here. First is the leading entry of each non-zero row is 1. Okay, so the leading entry of each non-zero row is 1. And each leading 1 is the only non-zero entry in its column. Okay. So the question is, what do I... First of all, like, what is the point of doing all of this? What's the point of having all of these? What's the point of having all of these restrictions, all these requirements? Note, the first three requirements don't require any entries to be anything, right? And then the fourth and fifth requirements require certain entries to be 1, and you aren't allowed to have non-zero entries below leading 1s here. Okay. Now, the easiest way to see what it is that's going on here is to look at a couple of examples. So in these two examples, you have two matrices in row echelon form. So recall our requirements here. So all non-zero rows are above any rows of all zeros. So in the first one, there's 2 rows of all zeros, and yeah, they're at the bottom. Each leading entry of a row in a column is to the right of the leading entry in the row above it. So the leading entries here are going to be the squares, assuming that these things are 0, that then being in row echelon form, it doesn't matter what these stars are. All these asterisks here, it doesn't matter what those entries are. This is in row echelon form. So then the last thing is all entries in a column below a leading entry are 0. That is satisfied here. Okay? It's also satisfied in this example, right? Note that here I have this entry, and it doesn't matter what it is. It doesn't matter what any of these entries are. My leading entries are these black squares. What matters is that whatever these black square entries are, below them have to be all zeros. Okay? Now, in this second line, these are in reduced row echelon form, or RREF. Okay? So, what is going on here? What is the difference? Notice that I've changed some of these asterisks, right? So some of these asterisks have been changed, meaning that, you know, it's not just up to me. They can't just be whatever anymore. So then what's going on here? Well, I have changed my leading entries. These boxes have to be 1s because that's required by requirement 4 here. The leading entry of each non-zero row has to be 1. Then each of these black squares has to be 1. There it is. Okay. But also I have this fifth requirement that each leading one is the only non-zero entry in its column. Right? So going back here to see the differences between these two things, up here, being in row echelon form, it didn't matter what any of these asterisks were. These two were both in row echelon form. But in the second line, notice that a lot of these asterisks actually have to be zeros, because this requirement that each leading one's the only non-zero entry in its column means that for all these black squares, those have to all become 1s, and then any other asterisk that is in a column with those has to become 0, right? But note that not every entry matters, right? So this asterisk corresponding to this entry here, actually it doesn't matter what this is because it's not a leading one. So it doesn't actually matter. Same thing with all of these, right? Because there are leading 1s in all these rows here. These aren't leading entries. It doesn't matter what they are. So these can be whatever. Okay, but you see that this is more restricted. Okay, so any matrix that is in either of these forms is said to have been row reduced. And so this thing that we were doing before is called a row reduction algorithm. Okay. So what is the purpose of this? So ultimately, the purpose of this is the following. So before, I was talking about how it is an annoyance, and it's a bad thing if I want to actually discuss the behavior of some matrix and try to come up with properties of that matrix. The fact that you can do this row reduction in so many different ways can make it hard to talk about what properties these matrices would have in common. Okay. So basically, the most important bit about this entire thing that I just wrote out is the following fact or theorem as it's stated in the book. So each matrix is row equivalent to one and only one reduced row echelon matrix. Okay. So this is very important. There's only a single RREF matrix that any matrix is row equivalent to. So if you have a matrix, say an augmented matrix associated to a linear system, and you apply the row reduction algorithm to it, okay, so you apply the row reduction algorithm to it, what that means is that by the time you get to, reduce row echelon form, that form, no matter how you got there, maybe you weren't totally efficient in the steps that you took, no matter how you got there, you are going to end up with the same thing as anyone else that got there, that got to reduce row echelon form through any other means. The point is that there's a single reduce row echelon form for any matrix. And so what this means is that while row echelon form itself may be simple enough to get you the solution to whatever linear system you're talking about, okay, if you want guaranteed uniqueness of the thing that you are looking at, you have to impose these last two restrictions. Now, the thing is that, again, as I said, you don't always need to put something in reduced row echelon form in order to solve it. We achieved answers to those two linear systems we looked at without putting it in reduced row echelon form. So a lot of times row echelon form itself is perfectly fine for actually solving it, and you would just put it in this form just because it's the simplest. Maybe you could answer it directly from here. But the point is that this process, this algorithm that you use to reduce matrices, it always terminates, and it terminates in reduced row echelon form. And what that means is that it terminates in reduced row echelon form, which is unique among any matrix that is row equivalent to that is going to have the same reduced row echelon form. So this means that there's only one answer to a reduced row echelon form for a matrix. So this is going to allow us to categorize and classify matrices that have the properties that we want. Okay. All right. So that is it. I think that Monday is Labor Day, so that means no lecture on Monday. So then I will see you all next Wednesday. And yeah, I will post to Elms. Whenever I'm going to announce something, I will put an announcement, so you're never going to have to rely on lecture to hear a homework announcement. So your first homework might be posted. I might post it next week instead. After we've done one good example of reduced row echelon stuff on Wednesday is when I'll post your next. What was written on the last sheet of paper? It was this, that each matrix is row equivalent to one and only one reduced row echelon matrix. Okay, so this is theorem 1. This is theorem 1 in the textbook in chapter 1. So anyway, I think that is I think that's about it. So I will see you all next week. See you all on Wednesday.